As we turn our attention to volumes, we're going to consider what happens when we take a region in the plane, for instance, this region under the curve f, or between the curve f and the x-axis, from A to B, and rotating it about the x-axis. The result is something called a solid of revolution. So think about this as a 3D object that's kind of round here. And in order to consider how we're going to come up with a volume of such an object, we're going to consider what happens with a representative rectangle. Now, this rectangle has a width of delta x, and as we rotate that about the x-axis, it forms a disk in space. Now, the radius of this disk is the height of the function, say f of x sub I. And just as we thought about adding together the areas of a bunch of rectangles to come up with the area under a curve when we first saw integrals, we're going to be looking at adding together the volumes of a bunch of these disks to form the volume of the solid. So let's consider the volume of such a disk. It's disk with a K, not C, not like a compact disk. And the width of the original rectangle, which we call delta x, is now the height of this disk. So this is our delta x there. And then the radius of the disk is the function evaluated at some point. So we can say the volume sub I, we'll say it's just the volume of one of these disks here, it's going to be based on the area of a circle times the height, right? So it's pi r squared, but r is f of x sub I, times the width of the thing, delta x. This leads us to something that we can write down. This is called the disk method. The volume of a solid obtained by rotating the graph of a function f from A to B about the x-axis is v equals the integral from A to B of pi f of x squared dx. You see what's happening is we're taking n of these disks as we go from A to B and adding their volumes together and then letting n go to infinity, and that's what we call an integral. We will of course see examples of this in a bit, but first I want to go to the next topic. Suppose instead of a region defined by a function in the x-axis, we have a region that's defined by two functions. In this case, we'll say f and g, where f is bigger than g. If we take a representative rectangle that forms that area and rotate it about the x-axis, the result is going to be what we call a washer. It's a disk with a hole in it. That hole is because of the gap between the region and the axis of rotation. The resulting solid of rotation also has a hole in it. In this case, it's a V-shaped hole, but there's a gap in the solid. The result in this case is kind of like a flying saucer with like a funnel gap in the middle. I don't know. But this pink thing, as I said, is called a washer. And just as with the first example there, the height of the washer is going to be delta x. But now we have two radii to think about. We have one that goes to the outer edge, and in this case, that's the function value for f. So we'll say f of x sub I. And then we've got another radius that goes to the inner edge, and that's formed by the inner function, or the smaller of the two functions, and so g of x sub I. In this case, an incremental volume is going to be pi times f of x sub I squared times delta x, the outer circle, minus pi times g of x sub I delta x. It's giving us the hole in the middle, right? So I take the inner circle and subtract its area from the outer circle, turn that into a volume. That's what we're doing. More formally, the washer method says that the volume of a solid obtained by rotating the region between two functions, f and g, between a and b, where f is bigger than g, over an interval from a to b, about the x-axis, and we get v equals the integral from a to b of pi outer function squared minus inner function squared whole thing times dx. And of course, we'll see examples of this in this series of videos as well.